So thank you everyone and for joining us today for this week's SEDS Online webinar. As always, we would like to thank our sponsors at IAS, which allow us to offer all of these resources free of charge. So this includes things like our lectures, our learning tools, virtual field trips, and in-person field trips now. So make sure you take a look at our website to see when we have new info and new stuff coming up on there. So today's lecture is Thomas Dodd, who is a sedimentologist at the British Geological Survey. Thomas got his master's degree at Keele University, and his research interests include deepwater sedimentary environments, processes, and products, specifically deep-lacustrine sedimentary systems, working on all sedimentary environments in a range of basin settings across the globe. So thank you very much for joining us, and I will hand it over to you.
Okay. I will share screen, reset, and pop that up. God. Just minimize that. Okay, just to check, you can see that, can you? Fine. Okay. Right. Without further ado, right, thank you very much to SEDS Online for inviting me to provide this talk for you this afternoon, or this evening, morning, depending on where you are in the world, I guess. Thank you for the introduction. I'm here to talk to you about hybrid event beds, and specifically hybrid event beds in the context of ancient deep-lacustrine fan models. And so hopefully over the course of the next 40 minutes or so, I'll essentially try and give you a sort of an overview of hybrid event beds, what they look like in deep lakes, and provide some potential new perspectives on them that might be specific to deep lake settings or just in general for deep water systems in general. Before I start, I'd like to acknowledge my co-authors on some of this from the BGS and from Keele University, and also Lawrence from UCD, who have helped with some ideas for the topics covered today. And one of the thank you goes to the Falkland Islands government for providing the data and allowing me to work on it and show things over the years. Let's transition. Sorry, the slide's not moving. There we go. So hybrid event beds. Overall background, just to dive straight into it. Some of you might be very competent in working on hybrid event beds, may have worked on them for years, are currently working on them. But for those of you who are not, just sort of overall what they are. Essentially, they're event beds deposited as during a single event that show evidence for mixed flow behaviour. That's a very, very simple generalisation of what they are. In actuality, they're quite a complex bed type. Broadly speaking, they're composed of a lowermost coarser grain unit, usually of sand, an uppermost unit of more mud-rich sand / siltstones, and then the trailing wake of the deposit of the H4 unit and perturbed H5 hemipelagic, or in this case hemilimnic fallout. And essentially there's been a lot of attention on these deposits over the last 10-20 years in one form or another. They originally were described and termed different names by previous workers. In 2009, Horton published the hybrid event bed model that previously they were called linked debrites, and from that point onwards they've been termed hybrid event beds, and so there's been a whole plethora of work done on these deposits from across the world. Some examples in here, just from Fanaso and Pierce, just show that a lot of work has been done on trying to understand the relationship between the sandstone and the overlying mudstone, and how both of those sort of key parts of this deposit were formed, what processes resulted in their deposition and what controlled their overall distribution and character. And a lot of work's gone into trying to map and follow out and predict how hybrid event beds are distributed in space and how they change both axially to laterally and also proximally to distantly within deepwater fan systems. I think the overall general model for the high density for the sand is that those sands are deposited by turbulent or turbulent suppressed flow. So and then typically that might be a high density turbidite that is forerunning. You have that H2 unit between the H2 and H3 units we'll get onto in a second. The H2 unit is viewed as a transitional deposit between the two flow types. And then the H3 unit is a separate part of the flow event, which is deposited in generally more cohesive flow, certainly a flow that might be more like a debris flow. So it's when we say these things are deposited by mixed flow behaviour, it is that these event beds show different flow types and preserve the product of different flow types during that one flow event. And I think it's teasing out the controls on how you generate a hybrid event bed. That's what I want to go over today, and specifically looking really, to be quite honest, at the H3 unit, the debritic deposit at the top. So this part in here, this interval in here. As I said at the start, there's a plethora of published work on it out there, and a lot of those published examples are from marine systems. In fact, a high proportion of them are produced for marine systems. There are published examples of hybrid event beds in deep lakes, but not a huge amount that goes into the detail of firstly, are those processes the same in a deep lake as they are in a deep marine setting? If they are the same, then what are the controls on those systems? But also, what are the differences? So why look at HEBs in a deep-lacustrine setting in particular, and why investigate the distribution and character of HEBs in the context of deep-lacustrine fan models? Well, as I alluded to there may be differences between deep lake settings, whether that be allergenic or autogenic controls on the system, differences between the deep lake setting and the deep marine. It might be simply scale, but also it could be other controls such as the type of water in the basin, variability and salinity, and how that might affect flocculation for the clay grain sizes. A whole range of different scales of variability in controls. And I think this is something that needs to just be maybe explored a bit more, and some of these controls vary, whether that be looking at ancient examples like I'm going to show you today, or whether you're modelling in the labs and trying to explore whether certain factors in deep lakes do control the differences in the products and processes, or the processes and products rather. So today's examples that I'm going to go through are from ancient deep lakes systems. They're from the North Falkland Basin. So I'll just give you a quick background into where that is and where these examples are from. So that's from the North Falkland Basin is just located here towards the southern tip of South America. And the basin itself is to the north of the Falkland Islands, so where my pointer is just now. The basin overall is a north-south trending fell rift graben with another trend, an older trend which comes through in here. But the key part of the story today is this north-south trending system in here. That basin itself, if you take a geoseismic cross section across the basin, it's a half graben geometry in some places and slightly more formed graben in other places, but broadly speaking, it's formed of a larger eastern graben and a smaller western graben out this side in here. The examples today are from the eastern graben through in here, and this polygon shows you sort of the location of the turbidite fan system, or one of the turbidite fan systems that I'm going to talk about today. that system is 10 to 15 kilometers long, depending on which part of the system you look at, but the largest extent is about 15 kilometers, and they're about 5 to 7 kilometers wide, depending on where you take that measurement as well. So broadly speaking, they're quite elongate systems, sometimes 2 to 3 times long as they are wide. And these fans were deposited in a deep lake setting during the early Cretaceous. So the graben itself was filled by a lacustrine system during the early Cretaceous. And from this part of the stratigraphy here, where my cursor is now, the orange polygons on the map, that orange polygon forms quite a typical steer's head geometry, signifying that it represents the early post-rift tectonic stratigraphic fill of the basin. And so these fans were deposited in these two intervals in here. The first discovery, hydrocarbon discovery in the basin, because let's not forget that's why some of these wells were drilled. The first discovery was the 1410-2 well, and that discovered the sea line fan, which I'm about to show you in a minute. So all of the data and interpretations are based on that data set, high quality data set that was collected for those purposes, but got a lot of good science out of it as a result. So I'm not too unhappy about that myself. So overall, stratigraphy wise, the fan systems from that zone in there, I've just shown you that. But just sort of honing into them now, because I've got to get down to the hybrid event bed level. So just to quickly go through, there's a whole plethora of fan systems out there. These aren't all of the examples. These are just from the eastern flank. And the key ones that I'm going to talk to you today are the sea line fan, the Casper fan, the Zebedee fan, and the Beverley fan. They're all early post-rift deposited in the LC3 unit. And they are sort of, the sea line is much older than the Beverley fan. This does show relative age relationships in space. If you look at them in plan view, they all come from the eastern margin. Just forget about rear for now. They all come from the eastern margin, are fed from this eastern flank, travel down into the basin broadly from these easterly located feeder positions. They follow a northeast to southwest sort of strike and have variability within that sort of directionality. And broadly, they go from being older to younger, heading towards the south. So there's a relationship in the facies belts moving towards the south of the basin. The examples today are these ones here, like I said before, from the strat diagram. The sea line fan covers this polygon in here. The Casper fan is this blue polygon that underlies the purple one. The Zebedee fan is the pink one, and the Beverley, the youngest fan, is the one that overlies it. All sort of similar scale, all similar sort of geometries with the same sort of scaling and the same sort of elongation to them. So very similar, very analogous fans in terms of the size and composition and internal architectures that I'm going to show you on the next slides. So here's the sort of perspective of the basin. Imagine you're in the early Cretaceous, and this is the deep lake setting. We have these features that I've just shown you as polygons in here. This is an amplitude map, seismic amplitude map, draped on 2-way time structures. So essentially, it shows you where all the high amplitude features are in the basin. The high amplitudes can be broadly related to more sand-prone areas, and the blues and darker colours, the purples are more mud-prone. If you remember that sort of rule as we're going through, you should be able to get an idea of what I'm trying to show you. So essentially, the brighter colours, the reds and yellows, are where there are more sand-prone facies. So this is the sea line north fan, the sea line fan, Casper, Beverley, fed from the eastern margin feeder system. They come into the basin and interdigitate with a delta that progrades in from the north towards the south. These are probably delta toe set deposits in here, and this is the lake basin floor. So they do interact along that feature in here. So that's sort of the seismic evidence base for the setting. Here's your 3D conceptual depositional model for that setting here. We've probably got sort of the delta sort of toe sets in here, and the rest of this is out of the 3D area. But most of that is shown in here: sea line north, sea line Casper and Zebedee is in there, and Beverly to the south. Broadly speaking, we think these fans are fed from a pre-sorted shelf-wall clastic system in here, some of which may have oversteepened and failed to feed some of the systems. Others might be more linked directly to the fluvial systems draining into the basin, and certainly you see a change in fan trajectories as you move southerly and move younger through the sequence, and that might highlight a relationship between the fluvial systems, but that's for another day. So we've got an environment during the early Cretaceous, an early Cretaceous lake with turbidite fans coming into it. This is a slide, a lot of information on this slide, but what I want you to get from this is the sea line fans. This is the amplitude maps, the same sort of amplitude maps as I showed previously of the sea line fan. And we can see in plan view, the seismic amplitudes show variability, but what they also show is not just variability, they show quite interesting seismic architectures, sinuous architectures, things at the end of the fan system that I call terminal mouth lobes. You can see in this map in here from the SL10 lobe of the sea line fan, quite sort of enigmatic feeder systems and outwards branching geometries. The amplitudes are representative of the architectures or the element level architectures within that fan or fan lobe system. So we've done a lot of work and interpreted them on the basis of that and looked at sort of axial areas, fringing areas and distal fringe areas. And we do have well control on all of that as well. So we know what's in all of these zones that we've intersected and been able to sort of check our seismic-based interpretations against the core data and sort of relate the two together, and then understand the distribution of the facies for the sea line fan. But they are quite tabular features in the seismic data. So you can see here's some examples in here of what it looks like. Essentially, one lobe is one reflection, and so we've had to map them out in plan view and very carefully sort of pick out where their lateral extents go, and then look at the amplitudes in plan views to sort of understand these systems internally within each sheet, which, by the way, they're not sheets, they're quite internally quite complex systems, but initially they were thought to be sheets based on the seismic interpretation. So I'll go to the next slide. As I said, those seismic-based interpretations, and I'm going to show you some examples with the context of hybrid event beds in the later slides, but first I wanted you to understand and sort of get used to looking at those data types. Those data types are and interpretations are underpinned by core data. There's 9 wells across the area, over 500 meters of core, but there are good intersections of lobes in different places across different fans. So the left image shows wireline log data that's been correlated for the sea line fan, and the black panels are where we've got core. So you can see that we do have representative core from different parts of the fan system that have been correlated. We've got a good control of where those cores are from, and therefore we can start to think about the fan systems in detail in terms of variability and sedimentology. So that's for the sea line fan. The right image shows the available core for the ones I'm going to show you today. So we've got the Casper fan, we've got core from 2 different lobes in the Casper fan, so CA10, 20 are 2 different lobes. We've got core from one part here and another part in here. We've got core from the Zebedee fan and core through the Beverly fan. So we've constrained it geologically using the wireline data, using the core data and the seismic to underpin all of that. But I think in this group we're sedimentologists and we want to look at actual cores through sedimentary rocks. That's probably what everyone here is interested to see and hear about. So I've shown you what the core actually looks like, and just to get you a feel for it. One of the key things of understanding hybrid event beds in the context of ancient deep lacustrine fan models is you need to first understand the deep lacustrine fan models. So we've done a lot of work trying to understand that as part of work we did in 2019. We've come up with a model for the deep lacustrine fans. They're largely composed of high density turbidites. So you can see some nice clean structureless sands here and here, the high density turbidites. They also have examples of more thinly bedded high-density turbidites and low-density turbidites from other parts of the fan. We have high-density turbidites with hemilimnic mudstones, so in less active areas. There's examples where there's not as well sorted or more immature high-density turbidites in more of the channelized areas, just where my cursor is here, and a whole set of other sedimentary structures within the coarse grain model. But within all of that, we do have hybrid event beds. So my cursor is just on a hybrid event bed in here. You can see that it's not just one, there's multiple stacked hybrid event beds as a sequence or succession, let's say. And that's within an interval of otherwise high-density turbidites either side. So essentially, we know that we see high-density turbidites, then hybrid event beds, and then high-density turbidites again. Why is that important? And this goes back to my questions at the start. Why is that important to understand? And it's because hybrid event beds can form baffles and sometimes barriers to fluid flow in the subsurface. So being able to predict, map, characterize, then also predict where they're going to be in the subsurface is really important to any project that utilizes that subsurface. So whether that be hydrocarbon exploration or CCS or for any other purpose, I think that it's quite important to understand where these things are located. And we know that they are within otherwise what we think are otherwise good reservoir intervals. And so their distribution and character does need to be understood. The next slide shows you more examples and just thinking about why they need to be understood further. Well, here's some more examples of where you see hybrid event beds in between otherwise HDTs, high density turbidites. The scale is interesting to look at. You've got quite relatively thin debritic caps on top of thicker bedded sandstones. In other places, you have quite thick, up to a meter scale debritic caps. So they, whilst most of the examples are quite thin in the order of sort of 5 to 10 centimeter thick debrite caps, there are much larger examples, and when you consider that, then that's when the reservoir modelling side of things needs to really sort of take into account where these things are, because if you've got thinner ones, there might be thicker ones out there too. So there's some more core examples of sort of the hybrid event beds around the high density turbidites. They're quite clean sandstones, and you can see that this oil staining in here fills the H1 units for the hybrid event beds. So this example in here, you've got quite clear oil staining in here, and the caps show less degree of oil staining towards the contact. So there is evidence that they do essentially control the oil fill, the pore spaces in these systems. So, as I was saying, we've got the whole range of scales of observation there. We've got the seismic scale, the wireline scale, the correlated wireline, the core scale observations. We've done all that. We've brought that together. We've looked at the overall facies models for coarse-grained systems in sand-rich systems in deep lakes. Produced nice models like this, like in the .SL 2019 paper. And so we've developed that for the different facies belts and mapped them out for the sea line fan and for the other fans in the basin, using the sea line as a direct analog, and plus the core data to validate that. But I guess within that sort of bit of study, the hybrid event beds were sort of brought in as like, oh, this is a bed type. And at that point, we thought that the hybrid event beds could coexist with perhaps this facies association, the lobe axis facies association, or the lobe fringe facies association for that matter, but perhaps didn't explore enough about where they actually were located, and then also what they were composed of and what controlled that. So we've been doing a lot more work in the HEB distribution and structure, and essentially looking at the models from Horton 2009, et al. 2009, looking at the overall structure of that seat succession and thinking, well, perhaps there's additional divisions in there within some of these units. Certainly the work back in 2019 sort of alluded to that there were. You can notice here there's three facies here, Fab 1 to 3. Terrible name at the time, facies argillaceous breccia. I would change it now if I could. But the important thing is to note that there were three intervals or three key subunits identified in that paper within that upper debritic unit here back then. And so that's made us go back and consider HEB structure in some detail. And so not just the distribution, but the internal structure of that hybrid event bed itself. And I think in these examples I'm going to show you today, we can show that there is internal structure within deep lacustrine HEBs within the H3 unit. Whether that goes through to marine systems or not is that's the next step of the workflow. We're gonna that'll be a bit more work to sort of compare and contrast the deep lacustrine models versus the the deep marine models and explore the similarities and differences. But I think first I need to get you to the point where you can see that those divisions are there. So that's kind of like a rumbled up, sort of a jumbled update of where we are with these examples, interpreting these examples, sort of exploring the coarse grain model for deep lacustrine systems. But now I'm going to look at the examples for today, which is the Casper fan. So the Casper fan up on the screen here is shown with the similar sort of seismic amplitudes in here. I put the sea line fan up just so you can sort of do the transfer from the amplitude maps and the interpretation of the amplitude maps to the other fans. I remember saying they were quite similar and in a lot of ways analogous, all of the fan systems on this margin. So we're using the learnings from sea line, taking them across the Casper, looking at the amplitudes, similar features, sinuous or low sinuosity architectures feeding terminal mouth lobes, so one here, here, and here, and another one here. That same elongation pattern and other interesting internal architectures that you see in the sea line fan as well. So you start to build some confidence up that these things are real and they do show sedimentary systems or facies belts. So on that basis, we color it up like we did with sea lion and produce a set of facies associations, I guess. So lobe axis, lobe fringe, and lobe distal fringe. And so sort of interpreting those architectures on that basis. And then most important of all, we've got some core from some of these architectures. So the first example, the core is from this well in here. And it's a really nice succession of high density turbidites. Amalgamated high density turbidites form the main part of the fan system. Definitely not the most interesting thing for this talk. So let's focus on the hybrid event beds. So around those high density turbidites, the hybrid event beds exist, I guess, below and above the deposit. And so you do get some hybrid event beds directly below, and I think that shows early activity of the system at that location at that point in time. And a few right below the fan system itself, so you're moving up the core this way, and then you go into the actual the fan deposit, the lobe axis deposit in here, where the hybrid event beds aren't present or are not preserved, and that might be due to amalgamation or just non-deposition. Towards the end, you start seeing the preservation of hybrid event beds again, and then as you enter the top part of that deposit, they're quite pervasive. You get multiple stacked, amalgamated, if you want to say amalgamated hybrid event beds here. You've got more than one bed, I guess. More isolated instances, but they become more persistent towards the end of that phase of deposition in the fan there. So that's from a lobe axis, sinuous lobe axis position, feeding a terminal mouth lobe. Quite an active location in here. You also have, and sorry, just before you move on to the next one, just look at the thickness. So you're looking at sort of 10 to 15 meters, I guess, 10 maybe meters of continuous section. Certainly for this part, you've got 5 to 10 meters of stacked high density turbidites. The grain sizes are fine to medium. So then if we look at the same fan system but go to the other well, which we've got through this lobe in here, there's quite a difference in sedimentology. First of all, the deposit itself is much thinner. We know it's thinner because we've got wireline to constrain that there's no more sand up here or down here. The grain sizes are finer, so these are very fine to fine, usually maybe a few mediums here and there, but yeah, mainly fine, very fine to fine. There is still amalgamated high density turbidites, but there's fewer of them. And so the sedimentology is quite different, as you probably expect, in this distal lobe fringe location out here. And importantly, even in this distal lobe fringe location in here, you still see hybrid event beds directly below the main fan deposit itself, between below the lobe axis deposits. So the initial ones are in here. They sort of become slightly more pervasive as you move towards the fan itself. The H1 unit, I think, thickens relative to the H3 unit in general. As you approach the fan itself, there's a pattern to it within the deposit as you're moving into it. The thing to take home from this one is that, unlike this position here, when you move to the top of the fan, you don't see the hybrid event beds preserved, or at least they're not preserved in the same character or same deposit style as you see in this location, which might speak to the temporal evolution of the fan and preservation of HEBs in certain parts of the fan system itself. So that's Casper. Beverley, I'm going to go a bit quicker through Beverley. So Beverley, beautiful seismic architectures, similar sort of features that I've been talking about in the previous slide. We're going to colour it up very quickly and interpret it based on lobe axis, lobe fringe, and lobe distal fringe. Amazing architectures, one of the nicest examples there. We've got core. So the core through the Beverley fan is from this distal location just in here, in this distal but axial terminal mouth lobe. I call them terminal mouth lobes. Some people call them terminal splays. I guess it's the same thing, different name. What do the deposits look like at this location? Well, we've not quite got the bottom of Beverley because the core stops just before the bottom of the fan, and we can see that in the wireline data. But the bottom of the fan is around here, I guess. So you've not quite got the bottom, but near the bottom. You've got quite thick hybrid event beds at the base of the unit. When I say thick, the H1 unit is quite thick relative to the H3. The H3s are rather, to some extent, relatively consistent. So there's a stacking pattern at the bottom of the fan. Going into the main part of the lobe axis deposits in this terminal mouth lobe area, stacked high density turbidites with some hybrid event beds in the middle. Maybe pauses in sediment delivery to this location might be controlling this. And then I guess then you go back into the units of stacked high density turbidites. This bit's not amalgamated, this bit is, I guess. And then as you move up, you have a few instances of HEBs. There's one here, and there's not really one again until right at the end, but then you get another pulse of a HDT at the top before the abandonment of the fan in that location. So the first example I showed you of Casper, we had HEBs in the abandonment phase. In this location here and the distal location of the Casper fan, we didn't have HEBs in the abandonment phase. So there is a temporal distribution of these HEBs, I think, and not just a spatial distribution needs to be considered. And I'll come back to that later on in the talk. So the final example is the Zebedee system. It's a slightly different system in terms of plan form geometry. It's got more of a, I guess, forked geometry to it, I would call it, or even if you're looking at the overall shape, maybe a funnel sort of shape. And the geometries internally aren't directly as comparable to the last two examples, but taking that these brights are sort of sinuous or gently anastomosing to some extent flow pathways within the fan itself. The well example we look at now is drilled from a lower amplitude area in between the highs. So you've got this lower amplitude area in here, and you see them in other parts of the fan, also in between the high amplitude areas. So I think it's not just an isolated area, it's actually representative of these lower amplitude splotches in quite a medial part of the fan. If we interpret it, I interpreted that as being like, essentially these are the lobe axis areas of that fan, and in between that we get these stranded lobe fringe areas, these areas within the fan system itself that aren't cut out or overtopped by lobe axis deposits or flows that would deposit lobe axis deposits, I guess. And these areas, you might imagine, might receive quite a diverse assemblage of flow types. You might get lower energy flows that are rapidly decelerating, potentially resulting in hybrid flow, other flow types in these areas. And that's exactly what you see when you look at the core. It's quite a thick deposit, so it's as thick as any of the examples I've showed you. I think the thing to take from this is that whilst you do have amalgamated high density turbidites in some places in the succession, the hybrid event beds are much more common in this location here. Exactly what you might expect, that diverse flow types to be preserved in this location. The hybrid event beds, again, are directly at the bottom or below the first instance of lobe axis facies associations. You see stacking patterns and relationships, so that upwards thickening of the H1 unit relative to H3, moving towards the fan system itself. So there's an interesting relationship in there. We have HEB, stacked successions of HEBs dotted throughout the deposit, throughout the fan, and then also quite thick HEB deposits at the top during the abandonment phase. So it's a location that's more proximal than those examples that I showed earlier, where you had quite thin, abrupt abandonment and no HEBs at the top. So there's an interesting spatial relationship and temporal relationship to be teased out there. So we've got HEBs from loads of different places, from loads of different fans. We've reconstructed where they're from within the fan itself and what the controls might be on that. And I'll come back to that at the end of the talk. Just to go over their overall texture and internal composition, what do they look like? We've done a bit more examination of the variability of those HEBs, and in particular the H3 unit, the debritic unit at the top above the H2 or H1 unit. The H2 unit's not generally present in most of the examples here, and that's actually something that seems to be true in most published examples of sand-rich systems. The H2 unit, the transitional unit, doesn't preserve or isn't deposited, I guess. So we have the H1 unit with H3 sitting directly above it. And the thing to notice from all of these examples is that there's textural variability within that H3 broad unit, and there's also sharp contacts. And so we've spent quite a bit of time mapping out where those sharp contacts are and trying to rationalize whether there are subunits within the H3 unit, and how many there are, and what their textures are. And so we've come to the idea that essentially there's three units, like I said earlier on, the FAB argillaceous breccia facies that were identified in the early part of work from 2019. We've carried that through and identified and confirmed that that probably was reasonable interpretation at the time. There are three quite clear discrete subunits of the H3 unit that can be identified throughout all of these examples within the 500 meters of core that we've looked at. So we've divided that into H3A, B, and C. H3C is in here. And the H3C unit in some ways is the easiest one to see. It's this sort of, I'll say starry night. I don't mean starry night as in a diamictite. I'll just call it starry night texture for now. This sort of dispersed muddy sandstone that you can see here. You can see that same sort of texture in this example here. and this one in here. Moving down the scale of easiness to start going to the H3B and A units, there's I guess those units look quite different to the H3C unit, but there are differences between the two themselves. The H3A unit has less dispersed mud in the matrix. The H3B seems to have quite a higher amount of that, and it's across a step, it's across a sharp contact. So we've been building up these examples of the different textures, lithological sort of compositions, but also the textures. So looking at where clasts are, the orientation of the clasts within those deposits, the sizes, the compositions. And this was quite a stark contrast between that in the examples of the H3A units and H3B units. And we've compiled that list to put it into a FASES table like we all like to do, and characterised it on that basis. But importantly, the contact between these units is quite crucial too. And so you can see there's sharp contacts in this example here. In the other examples, you can see the sharp contacts, and in some of them you can see upwards bowing of the substrate below the contact between the B and C unit. But moving on to the one on the right, this one's an interesting one, is that we have the H3A unit in here, H3B unit and the H3C unit, and all of them have some kind of angular relationship across that contact with the next deposit. So it says that you have different textures, different compositions across sharp boundaries. To my mind, I'm not sure how you'd explain that unless they were deposited as a result of one flow, but maybe different parts of that one flow, with some temporal separation, whether that be seconds, minutes, or what have you. I think that's to be discussed for another day. I think it's quite clear that the H3 unit is not, I guess, one single simple deposit from a debris flow that follows the precursor turbiditic flow as part of the hybrid event bed. There's more complexity going on in that H3 unit, and that's what I'd really like you to sort of take home from this today. As I say, this is published in the sedimentology paper Dodd et al. 2022. The references are at the end, and so you can go read all that up there. But just to confirm that to you, I've got lots more examples of this. So there's lots more examples of that. There's complexity within the H3 unit, and so we've used all those examples to really build that model, that FASES model that is published. You can go and look at that information there and read up on the descriptions for each of the A, B, and C units, and also, quite importantly, some distinguishing criteria for each one. And so these examples, these descriptions, these subdivisions are based on the examples that I've shown you today from the deep lake setting, and I think trying to marry that in with all of the stuff that I discussed earlier about the distribution of hybrid event beds in the context of the overall plan model itself. I think this is an important part of that story. So it's something that needs to be done at the same time, which is why I've moved on to sharing this topic now. But we've subdivided the debris flow part of the hybrid event bed and shown that there is variability. And so whether that variability is due to these being examples from deep lakes, I don't think I've quite got that far yet, but I'm sort of considering how you might deposit that sort of those subunits as part of a single hybrid event bed. That's sort of the next question sort of answer, I guess. And I think where I got to with it was that I thought perhaps that these are discrete parts of that flow event that you could deposit or at least segregate through what we've termed advanced longitudinal segregation of the flow. And by that I mean that the flow's been traveling so far that you've been able to separate the fines into discrete flow components, and then one flow gets deposited, followed by the next one, followed by the next one. And importantly, each one has different rheological properties from the next, which is controlled by the amount of dispersed mud and also the class component that's entrained in some of these too. So I guess we've shown that there are multiple components within the H3 part of the hybrid event bed in these deep lake settings. So the next stage where we'll be trying to explore how you might separate the H3 unit into separate flow units, and so that's for future work, I think. But importantly, bringing that all together, so the big scale stuff plus the subdivision of the H3 units, we've started to try and think about how hybrid event beds are distributed in a deep lake fan model, sort of allying where the HEBs are located in terms of the lobe axis deposits. Are they in the lateral fringes, in the frontal fringes? And when you see them, are they sand rich? Are the lower parts, the H1 units, sand rich, or they've got a lot of dispersed mud within them? I think that they seem to be more sand rich within the lobe axis facies association. And I think that's true for things that are proximal and distal, as long as you're in that lobe axis sort of system. When you step away from that into the lobe fringes, I think you start to lose some of the sand component to the H1, but then at that point, that's where you start to see this division of the H3 unit into A, B, and C. And then my only explanation for that is that these flows in the lobe fringe areas perhaps have entrained more mud and have been able to segregate, or they've incorporated more material. And essentially, I'm talking more about the distal lobe fringe in this example, by the way. These things have travelled further, and you've got more segregation. The time and the longitudinal processes have had the ability to sort the mud material into separate flow units. Going into the distal fringe now, we're starting to get very speculative in the models because we don't have as much information from these locations. But I'm working on the basis that you'll start to lose more of the sand component from the H1 part of the hybrid event bed, and preserve more of the mud-rich units as they may overrun or continue to flow out into the basin further. And then as you get into the lake basin plane, you might just see quite mud-rich HEBs. They may not even look like the HEBs that you saw over here. They might be very, very fine-grained, not too dissimilar from the hemi-limnic mudstones. And I guess that's where the work of people like the same 2020 paper comes in, looking at wireline data to try and spot HEB deposits from, or at least deposits from sediment gravity flows from the background sedimentation. So that's I think the distal part of the story is much harder to understand than or at least the distal lateral and distal frontal story is a lot harder to understand at this present moment in time than this part of the story where we have data for. So that's just the spatial distribution. We've got subdivision of the H3 unit. We've got spatial variability. To finally just sort of put it into perspective of the new insight sort of side of things, I think I've spent a bit of time, and I'm going to be spending a bit more time, so it is a bit of a work in process, thinking about the temporal distribution of hybrid event beds. There's a lot of statements out there that say you only see hybrid event beds in certain parts of the fans, and you can't possibly see them in other parts of the fans because you can't form them in those areas. In some cases, I don't necessarily think I think those statements are probably true to some extent, but when you consider a fan that's built up over a longer time period, perhaps by smaller flows, like we might have here, I think you can deposit hybrid event beds in certain parts of the overall fan. It's just that they were deposited during a certain period of that fan's deposition. So to explain what I mean by that, I'm just going to go through this very quickly. We'll come up with that model that you might have hybrid event beds in the early initiation phase of the fan. Certainly the evidence shows that we see hybrid event beds form just initially below, so in here, just initially below the main lobe axis deposits. And that probably is to do with the interaction with the virgin substrate and entrainment of muds from the topography and interaction with the rugose topography that might be there before the initial fan comes through. So those preserved hybrid event beds are shown by these sort of green colours in here. As you move into the growth phase, some of those hybrid event beds from the proximal part of the fan are eroded, I think, and those sediments are reworked and transported downstream during the growth phase. During that growth phase, I think there is possibility that you could form HEBs in the medial to proximal areas. But as you move through the fan itself, you then erode them subsequently during later phases of fan growth. And that's not across the whole fan surface, but I think you can deposit HEBs in the off-axis areas and the more proximal areas of the fan. It's just you don't preserve them. And then later on, during the fan's history, changes in the hinterland drainage system or even structural effects on the fan itself might result in bypass of this part of the fan. And so essentially, a lot of these areas in here become, let's call them interfluve areas for now. And those sinuous channels feed distally located lobes or terminal mouth lobes. So I've shown that very noddy schematically here, that you might have the early parts of the fan in here, and the later parts become bypassed, and you feed these terminal mouth lobe systems out in this part of the basin. So at that point, you start to deposit your hybrid event beds out in the distal part of the fan. Here, you preserve some of those out in this zone in here, in those distal extremities where we saw lots of hybrid event beds being found during the abandonment phase. The temporal abandonment phase in those locations might relate to just the preservation of the hybrid event beds and non-deposition of the abandonment phase, if that makes sense. But the key thing is to take from that is that the system backsteps, I think, and then you start to produce some hybrid event beds and deposit hybrid event beds in the more proximal parts of the fan out in here. So I think when you take that into consideration, you get hybrid event beds in certain parts of the fan, okay, and you've got examples from outcrop that show that. I'm not sure how that translates to when you then consider that the fan itself is built up over time. You might preserve earlier parts of the fan, you might erode them, you then bypass, you deposit out here, you backstep, you don't deposit out here, but you deposit out here. And so when you get a core, I guess my insight is that perhaps it's not as simple as that you see them only in frontal areas, for example. You might see them in other parts of that fan system that used to be frontal areas, that in areas that you've preserved those hybrid event beds and haven't eroded them. And going back to my comment on the stranded lobe fringe deposits, I think that might be a clue to how you could produce and preserve hybrid event beds in quite axial, quite proximal areas of a fan. There are published examples out there where people have found HEBs preserved in those locations, but a lot of studies do end up suggesting that you can't preserve them in those locations, when I think you can if you consider the temporal context of that fan system. So I'm conscious of time, but just to wrap up, and I'll go through those conclusions there in just a second. I think there's lots of factors to consider in terms of hybrid event beds, where they're produced, how they're preserved, their internal complexity, and what that might say about where they're produced and how far they've travelled, and so that might provide additional insights into predicting them in the subsurface. And that's where I'd like to go with the H3 A, B, and C subunit divisions, is exploring their character and distribution. But all of those factors may or may not be simply just found in deep lakes. It may be that you get this division of the H3 unit due to certain water salinities. You might interacting with the dispersed clay and some kind of flocculation sort of interaction. I don't know. I don't have the answer to that, and I guess that would be the sort of next step of exploring how you might produce these these subunits. But I think I can show that they do exist, and they are discrete units that you can map out internally within that unit. So that's I think that's pretty well constrained, and so we'll follow up on that. But I guess the next stage would be to sort of look to compare if you do get the subdivision in the marine setting, and if not, it might be that it is that you only see them in the deep lakes. I think you have to consider the temporal context of deep lacustrine HEBs, because the flows I think are in deep lakes are formed by much smaller flows. The deposits are formed by much smaller flows over longer time frames, perhaps, and so the flow scale flow processes in geology, I think, have a greater control on overall architecture and how that fan builds up over time, and that impacts upon where you find HEBs within the fan system. And then when you're reservoir modelling, that's very, very important to consider, because that might fundamentally change their distribution in your reservoir models from how you might have distributed them using the examples from the marine setting. So lots to explore on that. So just to actually just succinctly conclude here, hybrid event beds comprise the 5 internal units, including H1, 2, 3, 4, and 5 that you see in marine systems. H3 can be divided into A, B, and C subunits based on intra-H3 contacts and differences in the mud matrix contents of the lithological composition and textural variability and character. These subunits are interpreted to have been formed as a result of advanced earlier, rearward longitudinal transformation processes, and leading to a long flow segregation of H3 debrites into multiple flow components. That's the idea I'm going with. I'd love to talk to anyone who has any ideas further on that. HEBs are encountered and preserved in the lobe axis, lobe fringe areas of the 3 fans that we looked at today, but only rarely seen in relation to the hemilimnic mudstones. But that's because those hemilimnic mudstones are from the inter areas between those fan units. So more could be found in distal lobe fringe areas or frontal areas in the very distal extremities of the system, but we need more core data to prove that. And finally, HEBs are formed and preserved in the initiation phase, and where they're common and widely distributed in the data that we have. They're sometimes in the growth phase in certain areas on fan surface, like the stranded lobe fringe areas and fringing positions. That's lateral fringe and frontal fringe. And then also you see them during the abandonment phase as the facies belts retreat landward in certain parts of the fan and not so much in others, which is another interesting thing to explore and understand further. There's some references to at the top of what all this work's based on, and the others are what I've used throughout. So thank you very much for listening, and I hope to take any questions that you might have.
All right. Thank you very much. That was really interesting and a lot of really good data in there. So if anybody has any questions, please feel free to put them into the chat. Make sure you say who you are and where you're watching from. We already have a few questions, so I'll get to reading those. So the first one is from Jacobas. He says, thanks. Is there evidence in the cores for transient turbulent flow deposits, such as turbulence-enhanced transitional flows and lower and upper transitional plug flows?
I think that I've seen some examples, some very clear examples of that, yes. I haven't explored it. I haven't got any examples in that slide that I can really call on, definitely. But no, I'd be happy to chat about it further, Yako, actually. It's yeah, there are some things. I've seen the papers that you've been producing on those flow types, and there were a couple of instances where I was like, oh, that looks quite similar. So yeah, that's something to explore further, I think. Sorry if that doesn't answer it, but that's the answer.
Okay. Our next one is from Ross Campbell in Ontario. Thank you, Thomas. Great illustrations and fascinating interpretations. You show siderite nodules. Do you see any other orthogenic or early diagenetic concretions or cementation like other carbonates, pyrite, phosphatic nodules? And the bioturbation, is that in the muddy facies?
Yes, so the first part of that, yes, you do see lots of other just pyrite and such in certain parts of the hybrid event bed, particularly in that H3C unit, the upper part. That's where you see most of it being carried. Lots of things associated with, there's lots of plant matter and carbonaceous material within the H3C unit. And in association with that, you see the pyrites. Siderite nodules is really interesting because in a lot of those examples, it's difficult to, I think the one example, it does look like it might be sort of in situ or orthogenic. In other examples I've seen in this data set and lots of other data sets too, it looks like some of them are actually extra basal almost siderite nodules that have been carried in that flow. And I think more needs to be explored about that, to be quite honest, because there's so many examples of them shown, but I don't think anyone's really explored that too much. And then for the bioturbation, you see the bioturbation in the intervening hemi-limnic mudstones mainly, but some of the HEBs, the upper part of the H3C unit, particularly when you don't have a well-developed H4, that has some bioturbation in it, and certainly that bioturbation extends into the upper part of the H5 unit, the sort of hemilimnic perturbed rain out sort of facies. So yeah, that's where the bioturbation is. Yeah.
All right. Our next question is from Howard Billman in Fort Collins. How thick are the hemilimnic muds, and where do the muds come from? Is it possible this is levee?
Yeah, that's a good question. That's a really good question. They're very thick throughout the basin. The sections of hundreds of meters of thickness, if not more, of hemilimnic muds encasing the turbiditic sequences. Internally within the fans themselves, some of the baffles in some of the wells are up to 1 meter, 2 meters thick. Where does the mud come from? It could be that you build a fan up over time and you can have periods of temporary abandonment. I think you do build these things up over long timescales with small flows, and you could abandon certain areas for considerable amounts of time that would allow the preservation of limnic fallout. But as you say, it could be that some of these muds might be muddy plug flow sort of deposits, I guess. I think more needs to be done on that one to fully, and we're going to look at that a little bit, looking at some of the wireline data next to try and explore whether we can see clear parts of the hemilimnic mudstones that are significantly different, because visually it's very difficult in the core data that we have.
Interesting. And then he had a follow-up question is, does the bioturbation suggest marine salinities?
I don't know is the straight answer to that. I think there's evidence from some of the biostrata of variable salinity. Some of it is quite fresh, and other parts of the succession is brackish. So I think you could have periods where there's a bit of evidence that maybe there was a bit of marine incursion into this lacustrine setting during, I can't remember which fan it was, but yeah, there is some evidence in it that you do have varying salinity. So yeah, I take your point. That's a good point.
All right. So I think we'll probably wrap it up there. That was a great presentation and lots of good questions. So thank you very much. And please, everybody, come join us on January 24th at 4 p.m. UK time for a recap on the 2023 IAS Summer School. So thank you.